Okay, the first thing we want to do is define a pin. So define ACS712 and the pin is A0. Then we want serial.begin 115200 or whatever baud rate you want to choose. Then down here we need serial.println analog read and then whatever the pin is, which is ACS712. Control T, Control S. I always do that. So Control T, Control S, and when I upload this thing, which is now, we should get an output near 512. So the radiator's on, but it's on very low, so there won't be many amps running through this thing. But let's just see anyway. Okay, it's done uploading, and we should get 512, and we do get somewhere near that. It'll be going all over the place, of course, but we do get 512, so we can carry on. We know this thing's working. So what's next? What we want to do is we want to measure this thing. Well, we want to take a sample every millisecond, really. So let's carry on. So if millis is greater than the last sample plus 1 millisecond, then take a sample. Take sample. And of course, last sample is a variable, it needs to be set up here. So long last sample equals 0, we'll say 0 for now. Then last sample, so if whenever we take a sample, we have to update this. Last sample equals the time now. So what this does is the loop runs at a crazy speed. It runs faster than a millisecond, but we only want this code in here to run every millisecond. We don't want it to go crazy and take millions of samples. We just want one sample every millisecond. So this will probably run and it'll say, well, the time now is still less than a millisecond, therefore a sample is not due. Anyway, let's carry on. So now we need another long, we want sample sum. So sample sum, and that might as well equal 0 as well. It doesn't actually matter, but sample sum. Now when we take the sample, we want to do something before this. We want to mess about with it, basically. So if I just the reason being is because the ACS712, it outputs a value from 0 to 1024, and 0 means minus 30 amps and 1024 means plus 30 amps. The middle value, which is 512, means 0 amps, but we don't want 512 to be, to represent 0 amps. We want 0 to represent 0 amps. So what we have to do is take away 512 from this value. We may actually have to add it instead, but we'll see. I'm going to take it away. So to check, let's just do it let's keep it simple and just say take away 512. So we'll leave the sample in for the time being, and it can carry on doing it at the crazy speed it does it. Let's just check that this works. So I'll upload again. So now what we should see is that it will output a number around 0 instead. And it says done uploading, so let's see what it's doing. That looks about right. I mean, it's hard to tell with it going really fast, but it looks about right. So take a sample. So where are we up to? So sample sum. This sample sum is going to basically sum all of the values together. So there's actually something else we've got to do before that, but let's make a start anyway. So sample sum equals, it's going to equal something in just a moment. What we have to do is, do you remember I said about the two methods? There's the RMS method, so I'll just write down here RMS method 1, and the other method, method 2, is the 0.707 method, which is method 2. What I'm going to do to start with, I'm going to show you method 1, and in method 1 we actually have to square the values in order to make this thing work. It's a bit silly, a bit strange, but anyway, let's get on with it. So we need to copy that bit of code, and sample sum equals the reading squared. Now, for those of you who know, it's actually really easy. You can, to square a number, it's the number multiplied by the number. So if I was to do this, analog read, blah blah blah, get the number, and then multiply it by itself, that's the square, but there's actually an easier way of doing it than that. So all we have to do is this, squ, and squ means square. So Control T, Control S. Now there's another thing we're going to do. In the loop, if the sample is due, we're saying get the number from the ACS and take the 512 away from it to get it to get the starting point from 0. Then we square it, and then we put it into the sample sum, and then the next time it will repeat and repeat and repeat. But as you can see here, RMS, and if you've listened to the previous videos that I've done, you'll know that to be able to make RMS work, you've got to square it, then mean, and then basically there's the root element as well. So we've done square, and then we'll need to do mean. But in order to do mean, mean is a mathematical algorithm, if you like, to be able to get an average. And the way the average works is that you get all of the different samples, you sum them all together or add them all together, and then you divide by the amount of samples afterwards. So what we'll need to do is keep track and keep adding and adding and adding all of these samples together until we've got all the samples we need. So what I have to do is I have to do this, plus equals. And plus equals means every time this thing repeats, keep adding to. So that means basically sample sum equals sample sum plus that. Anyway, thought I'd just clear that up. Now we'll add something to count the amount of samples. So down here we'll say sample, let's say sample count. So sample count plus plus. Sample count plus plus. The plus plus operator means add 1 to sample count. So over here we'll have another one of these. This doesn't need to be long. Then again, int is actually sometimes the same size as long, but whatever. Sample count plus plus. Right, so now how far have we got? So take a sample, add the sample to the collection, if you like, and then increment the sample count variable. And then what we want to say over here is that if we've reached 1,000 samples, so if sample count equals 1,000, then do something. And this is where all the averaging, let's say averaging stuff, goes here. Oops. And now we need to carry on with the calculations. So I suppose we could test it here actually. Should we test it? No, I suppose not. So sample count equals 1,000, and what we want to do is we want to print out some results and carry on with the averaging. So so what do we want to do? We want to get this, let's say the average. So we want, I suppose we want a float here. So float mean equals the sample sum, which is all of the samples added together. So we want to get sample sum, and then we want to divide by the amount of samples, which will be over here, which should be 1,000 anyway. But so the mean equals the sum of all of the samples divided by the amount of samples. And what's next? So up to now we've squared, we've got the mean. Now what we have to do is get the square root of that, and let's say float, what do you want to call this, I don't know, final value really, or something like that. Let's just say value. It's not a very good name, but whatever. So value equals square root of the mean, and this is basically the RMS calculation. And what that should do, oops, I've forgotten equals there. And what this should do is do the RMS calculation on all of these values and give us the end result. Now over here I'll print out value. So just to make this a bit easier, the final RMS value is string, oops, what have I done there, string value. So yeah, it does all its calculations, does the RMS, and it should give us the value here. We're still not finished, but this is the first major step. So now I'm going to upload this. Oh no, there's one more thing we need to do actually. We need to reset the values. So over here, sample sum equals 0 because we need to reset it, and sample count also equals 0. That's to reset it, so the next time it goes through the loop, it can start again. Now this gets a little bit complicated, but I'm not going to actually explain all of it. Float voltage per count or voltage per point or whatever is 4.8 millivolts per count. Now the reason I know that is because if I go to calculator here, has it come up? Where has it gone? Ah, here you go. If we get 5 volts and divide it by 1024 counts, which is a 10-bit ADC, we get, oh that's strange, hang on. 5 volts divided by 1024, that's how many volts each count. So I said before the 44 counts, each one of those counts corresponds to that amount of voltage. So yeah, if I just copy that, I suppose we'll paste that there. So that's the amount of voltage. Now it would be better if we got this in millivolts. So so if I change that into millivolts, there we go, that's better, and save that. So what we've got to do basically is convert the counts into a voltage. So that's how many millivolts there are per count, so we should be able to easily work it out now. So we'll add another one of these down here, and I'll comment that one out actually, and I'm going to say the final RMS voltage is, and now here we want to get the amount of counts, and each count equates to that. So value, the amount of counts multiplied by the voltage per count should equal the amount of voltage in millivolts. So let's try this again now, and this will be the amount of millivolts. So I'll just re-upload. Oops, I've just forgotten to add string to this thing. That's it, re-upload. And that's done. So Control Shift M, and now we should be able to get the amount of counts expressed as millivolts. So the final RMS voltage is 213 millivolts. So if I was to get the voltmeter now and check the amount of millivolts going from the ACS to the nano, it should read 200 millivolts. So I'm looking at the datasheet now for the ACS712. Now if I go down to my one, it's the 30 amp one. You can see here that the sensitivity is 66 millivolts per amp. Now there's just something I've got to say about this here really. Because I've got this measuring AC, it's actually not ideal, because with AC devices and stuff, you're not really as likely to measure high amounts of current, because to be able to achieve an amount of wattage with a high voltage, it means that you need less current. But if I was in a DC application, for example, then it requires a lot more amperage, lesser voltages to achieve the same amount of wattage. Now I don't suppose it matters too much if I've not made that perfectly clear, but basically it's unlikely that I'm going to ever reach 30 amps using AC, especially because my house has an RCD and an MCB which will probably cut off at 13 amps, but I'm not 100% of that. But regardless, the main point is that the sensitivity of this little ACS unit is 66 millivolts per amp. So I just get rid of that now. 66 millivolts per amp. So we've got the amount of voltage, but now what do we need to do? Well, we also know that there are 66 millivolts per amp output from this thing. So if I copy that line again, comment it out, go down here and paste. There are 66 millivolts per amp. So let's put another one here. So float voltage equals voltage that we've just worked out. And now what we want to do is we want voltage divided by 66 millivolts. Now this voltage is actually in millivolts, so I don't want to change it to millivolts. Yeah, I suppose I will. Millivolts equals the value which we did before, and then we want to do the amount of millivolts returned from the ACS divided by 66, and that will give us the amount of amperage. So the final RMS amperage is whatever. So Control T, Control S, Control U. Let's see what happens now. Okay, it says it's done uploading, so Control Shift M. And it's saying the final RMS amperage is 3.23 amps. So now I suppose it's the moment of truth. I mean, does that make sense? Well, I've got a radiator on its lowest setting, and that would mean 3 amps at 250 volts, which is around about 750 watts. And does that make sense? I suppose it does, but I'll just go and check. Okay, I've just gone to check on the label of the radiator, and that does make sense. So it's on its lowest setting, 750 watts or thereabout, does make sense. But anyway, let's just change this a bit. So I'm going to say the final RMS amperage is amount of amperage. Then I'm going to say over here, I don't know, let's say approximate wattage or something. So approx wattage, might as well do that in caps. Approx wattage is, then we want, well, in fact, I think it's time to put another variable in here. So we've got float amperage equals this. Then we want amperage in here. Approx wattage is the amperage multiplied by 250, because I'm in the UK, 250 volts. And then we want to add string to that, otherwise I doubt it'll print out. So the approx wattage is, and then we want to add a full stop to that, upload, and let's see what happens now. Right, Control Shift M. Right, so here we go. So the final RMS amperage is 3 point whatever amps. Approx wattage is 800 and whatever watts. So right, that's looking good. So apparently I'm drawing 800 watts right now on radiator. And what I'm going to do now is I'm going to turn the radiator up and let's see what happens. Now I've looked at the label at this thing, of this radiator, and it says the wattage, the top wattage can be around 1700 to 2000 watts. So I just need to do a calculation before I actually turn this thing up. So 2000 watts divided by 250 should be 8, is it? Yeah, 8 amps. So this thing could potentially draw 8 amps at its maximum setting. So I'm going to turn it up and let's just see what happens. Okay, so I've turned it up now, and you can tell straight away. So this thing is now drawing 5.4 amps, and it's all of a sudden getting really hot in here, and it's drawing 1.3 kilowatts. That's interesting. So I'll turn it up one more now. Now, 8 amps. I don't think I'll be tripping anything at 8 amps. Although it is quite excessive for well, you know, whatever. So let's just turn it up now. Yeah, so perfect. 8 amps or 8.3 amps, and the watts are around about 2,100 watts, which, okay, I believe that might be slightly over what it actually is. I don't know though, this could have been labelled incorrectly or whatever. So there you go, it's sensing 8.4 amps, 2 kilowatts. Now I've got an explanation for that actually. Over here I said amperage multiplied by 250 volts. Now it could be that I'm getting 240 or something, and that would probably make sense. So I don't know, delete this. 8 multiplied by 240, yeah, I don't know, who knows. But anyway, that's method 1 on how to measure RMS data. Now I'll show you method 2 of how to do it. So let's just close this off.